I'm happy to start then. So
Yeah.
yes, my talk today is going to be about automatic differentiation of Rust with the friendly help of your compiler. So to start with a little bit about myself, I'm an incoming master student at the University of Toronto. Right now I'm visiting the MIT Julia lab, so I got a bit of experience from the other side. Also pretty happy that we had some Julia speakers here, which made some comparisons. I did start my computer science research with HPC and machine learning, and at some point got in contact with compilers, which are kind of my day-to-day topic since then. So I've been working on this project together with Lawrence Schmidt. He's a PhD student at FAU in Germany, Erlangen-Nuremberg. He developed an earlier prototype of the work I'm going to present today, and for the last years we've been iterating together on some of these projects. So he's usually focused a bit more on the Rust front end, so the side which users are going to experience, while I'm working a bit more on the back end. And I hope I can give you some interesting insights on both the back end and the front end of our new auto-diff tool for Rust. So the first question, why do we even care about this topic, automatic differentiation? Some people might have heard about it. It will give you gradients or generally Jacobians, Hessians, whichever variations you want, which are used widely across science. For machine learning, we had yesterday a talk which was about gyro NN, so neural network library, and they use back propagation in order to update their weights. They have to know how to adjust those in order to solve their tasks and reduce the loss. There are more topics like Bayesian inference, uncertainty quantification, and generally for scientific computing, we do have a lot of simulations where we need to adapt some parameters. So given that we do care about automatic differentiation, what do we have at hand right now in the Rust ecosystem? So the two largest projects I'm aware of are both Burn and DFDX, which are both in general machine learning frameworks. So you can build your own neural networks based on those libraries. Burn itself has a backend which is based on PyTorch, which is pretty major. So you can do a lot of operation on that one. And since PyTorch itself does support automatic differentiation, you can kind of use it through that. But then again, you have to deal with the Python backend. So it would be nice if we had a proper Rust solution. They are working on allowing the users to use automatic differentiation based on ND array types. That's slightly work in progress, but it's improving. And on the other side, we have DFDX, which as a really interesting feature, which I find pretty interesting, has compile time shape checking. So if your neural networks would, like in the case of PyTorch, crash at runtime at some point, if you're lucky early, if you're unlucky after a day or two of training, well, DFDX can prevent that by using the Rust type system. They also do have some CUDA support, which you'll obviously want for running your networks on GPUs and making all of the training process a lot faster. So we do have some libraries available. Why do we need another one? So let's give an overview of how we can see autodiff toolings like Burn or DFDX or even most other languages. They take one input language, let it be C++, Julia, or Swift, transferred, so they kind of rewrite your code in order to get some code that is going to calculate gradients for you. So the output is still going to be whatever you've fed in there. So in our case, it will still be Rust code. We then have a Rust compiler, rust-c, which is going to lower all of the code. By default, it's using LLVM as a backend. So that's what we are going to discuss today. There's some work in progress to use different backends like GCC or Cranelift, but that is what we are using nowadays in Rust. And once we load it into an intermediate representation of LLVM, we do the final code generation, which is giving us a binary that we can later run. So are there any issues with this proposal? Is rewriting our Rust code into Rust code really the best we can get? And I do have a small case study here about vector normalization. It's a really trivial code. You can see it as a placeholder. Usually when you write larger simulations, which might be hundreds or thousands of lines of code, you might not be able to optimize every single line to the extent which you would be able to optimize this case. So let's assume we do have a function here which is trying to compute the norm. We got kind of sloppy over the day, and it's O of n squared. The reason is, well, we update each element of our output vector, based on the input vector, which we divide by the magnitude. And the magnitude itself is calculated in O of n. So we have a loop which is running in O of n, and we do have our magnitude, which is running O of n, which gives n squared. There's a trivial optimization which the compiler is going to do for us, even if we forget to do it ourselves, and that is move the expensive operation out of the loop. The reason being, well, we are not using I in this call, we're just using the whole array, so that's pretty easy. There's no dependency which prevents us from just moving an expensive operation out of the loop and caching the result. Now, how does it look like in the context of AD if we have such optimizations from a compiler? So we start again with our simple for loop. We try to like update each output element. We optimize it through the compiler, and we now differentiate it. It's not that important how like a tool is going to rewrite your gradients, but let's just trust the tool in this case and say that we get the right code out of it. So as some small context, usually we use reverse mode AD, especially for neural networks, as it's the most efficient. And one of the properties is that it might reverse the order of your code execution. So that's the reason why our magnitude here went moved to the end and why we are iterating in the reverse order. But those are technical details. And the key aspect is still we have our expensive gradient for the magnitude calculation outside of the loop. And we have a small loop here, which is just calculating some updates for the res, and it's still a loop in O of n. So how would the same behavior look like if we compare it to, let's say, Burn or DFDX, which have to operate on source code? Source code is not getting optimized by the compiler. So what we do have in this case is, well, they differentiate the code they see, right? So they do have an expensive magnitude operation inside of the loop, and therefore that is going to get differentiated to a slightly different code. Now we have the gradient of the magnitude inside of our loop, and in the primary case, we have seen how the compiler is able to move our expensive calculation out of the loop. But what happens here is kind of unfortunate for us. We do see that our gradient now looks slightly different, and we do see a dependency here. The reason is that, well, we had the same up. So the reason is that we have a dependency here of the variable which is dependent on I, which is our loop index. That prevents our optimization called loop invariant code motion, because moving that operation now outside of the loop would break our the gradient. So there are more cases like this, which generally make it preferable to work on optimized code. And that is what Enzyme is doing. So we can take whichever input we want, still like Julia, Rust, or C++. We will lower it into LLVM, run all of the optimizations. There are more than like the single example I just gave you. And then we differentiate our optimized source code. And just to be sure that we're really going to get the best performance out of it, we optimize the second time. So that's slightly unlucky with respect to our compile times, but the performance is pretty nice, as you'll see on the next slides. And well, from there on, we can just leave the rest to LLVM. It's going to go through the same code generation as the normal compilation process of Rust. So we did some benchmarks. Those are unfortunately not against Burn and DFDX, because there are like still some limitations to our Rust front end. But instead, we have two C++ autodiff tools, which like years or decades of experience. So we could assume that they do have some amount of performance optimization as far as it's doable on source code level. So we do have a reference setup, which is still using Enzyme, but it's differentiating our code before we are able to optimize it through the compiler. So that is kind of as good as we could get if we were not part of the compiler, given like optimizations and implementations which we have used for Enzyme. The speedup which we've seen for this setup is a factor of 4.2 against our own reference. It might be slightly higher against some of the competitors. So you see, like this benefit only comes from running the same set of optimizations and autodiff rules after optimizing versus running them before optimizing. We have carried out a couple of more benchmarks because those are pure CPU implementations. Once you run your code on a GPU, that those improvements become like orders of magnitudes instead of a single factor. The reason is that we also heavily optimize for memory usage, which makes GPUs benefit even larger. Yeah, so that was a bit about like how we can use a compiler in order to get our auditive framework up to speed. But obviously, what I presented right now was a general compiler, like LLVM-based tool. How do we get that into Rust itself? So we do need to provide a Rust user interface because, well, the first front ends which we had for Enzyme were based on Julia and C++. Rust has like some different semantics, so we want to be nice with them. The next question is, can we guarantee Rust level safety? I mean, one of the unique features of Rust is that if your code compiles, you can be kind of sure that you will not get seg faults. You hopefully will get the right result. And if you made some silly mistakes, either the compiler or like Clippy are going to hint you on that. We are working pretty late in the compilation process, so we do not really know about any specific Rust semantics. We cannot really directly interact with Clippy or like any of the user front-end facing tools. How can we still make the user have a nice experience? And how about our compile times? Rust has some larger compile times due to some of the checks which we have. Is it getting even worse? And well, the final question, right now we have a nice prototype. How can we make it available for everyone? Because DFDX and Burnens are tools which are already out there. If we just have a prototype in our own lab, that's probably less interesting for most of the people. So as mentioned before, Lawrence and I did a couple of experiments how we can integrate both of them. And there are a couple of issues. So the first one, Rust is composable. Sounds nice for the user because we can just easily publish grades. We can use grades from someone else, but it also separates code from us. If you use C++, you usually have like all the code rendered yourself. You all have a single compilation process, and you are easily able to inspect all the LLVMIR, which a compiler is generating for you based on your C++ code. With Rust, we have different compilation units, which are grades. And well, if we just get the source code for our current grade, that's nice because we can differentiate all the functions which you implemented in your current grade. But if you start calling a function from a different grade, we suddenly lack the LLVMIR, so we can't give you any grades for that one. And there's even a harder limit for us. We by default do not get the LLVMIR of the standard library. So every single function which is part of the Rust standard library becomes non-differentiable for us. That's obviously a blocking issue. So how can we work on getting all the LLVMIR without breaking the whole compilation process too far? And the other question which we had, how can we get the type and the layout of all variables? Because it's pretty obvious that like if you have an array of, let's say, 10 float values or 5 double values, they might have the same size in memory, but they do have different gradients. Or to give you even more extreme example, if you have an integer of 32 bits and some float values, well, they do have the same size in memory, but one of them can get a gradient, the float value, because you can like slightly adjust and analyze how it affects the output. Then you have the integer, which you can't really differentiate with respect to because you can't really do slight adjustments to an integer. So how do we get all those type and layout informations? For types which are compatible to the C API, that's pretty easy. They are standardized. They're not going to change. But even if you look at basic Rust types like a vector, those are not strictly defined, and they do occasionally change their layout release by release. So those are a lot of information which we need to get. And the first approach, well, it wasn't the first approach, but one of the early approaches was integrate into Cargo. It's our build system, so we should expect that we are able to get all of the LLVMIR code, and we kind of were. This is our nice compile command, which we gave to all of our users in the past. It was emit LLVM bitcode, which is some representation of the LLVMIR, which we can differentiate. We use our own cargo.plus-enzyme, so our own compiler toolchain. We do use a nightly flag called build standard, which is going to cause Rust to not only compile your source code, but it's also going to compile the whole standard library. So it will increase your compile times. And finally, we are not telling our build system Cargo to run our code. We just call Rust directly to make sure that we can even pass even more like magic flags. One of those is debug information. The other one is that we tell our compiler to not link our code. So we do end with some bit code for every single grade. We can then effectively replace Cargo from that point on. So we do link all your like single grades together. We have debug information from which we can try to guess the type of your variables, and we can differentiate that code. It did work to some extent. Debug information helped us to understand some Rust types, but again, the layout of many of those is not specified, and therefore it will not show up in debug information. So that was kind of limited. There were quite a few Rust types which we couldn't support, and you don't need an AD tool in Rust if it only can differentiate C types, right? So yeah, also the nightly build standard flag is interesting to get the LVMI of the standard library, but stabilizing this option is an ongoing process and it's not that easy. So we finally decided to deprecate this whole approach altogether. What can we do instead in order to combine our enzyme and Rust work? So we do have a new prototype, which is still a custom toolchain. So you can take cargo about your custom toolchain using the name of that, like plus enzyme in our case. We now fall back to the default operations like build or run under release mode, hopefully, in order to get some decent performance. And well, we are now part of the Rust compiler, so we do get all of the LVMR of the standard library for free. You do not have to rebuild it anymore. We get variable types because the compiler is obviously going to know about your types. So it doesn't matter if you use types which are comparable to C ABI, if they have another layout, if they follow the Rust ABI. We do still have some requirements which will break your compile times, which is specifically called ATO, like link time optimization fed. So that is going to cause the compiler to integrate all of the bit code which we need for our AD part into your binaries and into your intermediate artifacts. So yeah, that is our current approach here. You can see it there. Now, obviously, we do still need to provide a Rusty interface for all of that, even if we manage the compilation process, even if we manage the build integration. So let's look at like some really nice Rosenbrook function, which is just trying to like update our result variable with a couple of operations. That's pretty normal, and we now want to differentiate it. So we do want to know for each of those entries, each of those two entries of our variable x, how does it affect the output? And the design of our autodiff tool, which we used to come up with, was we do have a procedural macro. It's not a pure user-side procedural macro. We do still need a couple of fancy Rust internal tricks, but it's pretty nice to like and pretty close to the standard interface in our opinion. We still like to receive a lot of feedback on this one. So you are able to give the name of the function which enzyme is going to generate for you. You are able to decide where you want to use reverse mode AD or forward mode AD, which are like technical details, and it mostly affects the performance based on like how large is your input dimension and how large is your output dimension. If your output dimension, like in this case, is pretty small, a scalar here, and you have a vector as an input, you usually want to use reverse mode. And finally, we do have a couple of technical details like selecting if the output is active or inactive, selecting for which of those inputs you want your gradients. Here I picked a pretty easy example. We just have one input variable, so we mark it as duplicated. And that means enzyme is going to generate a new function for you, whose name we gave here. It is going to take, again, x as an input. It's going to do almost the same amount of operations here in order to calculate your initial result. And it's along the way calculating your gradients for this variable x. So in your main function, you suddenly have a new function, d_Rosenbrook, which you can call with your variable x, which you can calculate with some shadow variable, which you usually want to initialize to 0. And well, that's still a technical artifact, which we hope to remove in the future. So enzyme is then going to update both of your entries of dfdx with the corresponding gradients based on that function. That is working nicely if you do have direct access to your source code, like this Rosenbrook function here. But we've noticed that there might be an issue if you are trying to differentiate a function defined in another library. So we've been trying to come up with a second interface to give you some selection. And this one is, well, this example in general is a bit larger. So we do have a function called sign now, which is not working on like a single variable as you've known it, like from the standard library sign function, but instead it takes a whole input vector. We've just been playing around with it a bit. So we do apply the sign function here element-wise. We do sum it up after mapping our sign function over the whole array, and we do modify our output variable. So now we want to differentiate that sign function. We still want to use reverse mode because we have a single output, even if it's now passed as a mutable input argument. We do want to set a couple of how details that effectively was marking the non-existent output as constant. We do want to have the gradients with respect to x and y. So we now get our Jacobian function, which again has some shadow variables here, as you can see. Now, that would also work if you don't have access to your sign function yourself. So it's easy to see, we just provide the name here. If you were to differentiate a function from a different library, you could give it a path or like some specifier. Same for like standard library functions. So you could specify them the way you want to make them unique. And we would be able to look them up as part of the compiler. Now, we're going to fill, one of the things I should note, that's similar to C++ function declarations. So you see, you don't have an implementation of that function here. That's going to be provided for you by the compiler. So you don't have to worry for it. And you can just call it directly in your main function if you want. The other thing is, for some of those scientific codes, we might not only want like the direct gradients of our functions, we might want to have some higher order autodiff. So we are also able to differentiate functions which do not exist yet. So the Jacobian is going to be generated in the compilation process, but we can still pass it into our autodiff marker in the same way as any existing function. And we need to take care on our side then to just differentiate functions in the right order. We don't want to differentiate an empty Jacobian function before it's being filled. Well, differentiating a second time is going to give us a Hessian. You can see that those function declarations do get ugly over time if you add enough iterations, but well, here we have a simplified example on how to call this Hessian. And again, like this is the second interface which we have to our AD tool. Yeah, I have a couple of minutes at the end to discuss our design. So if you have a feedback on how we could make this a little bit more rusty, we'd be happy to hear. But before I do have to add some points which were slightly hard for us because they were Rust unique. So Julia and C++ kind of expect the user to do the right thing. On the Rust side, we do have a friendly compiler which is going to stop you from shooting yourself in your foot. So we don't want to break that property. Now, I do have an example here where we pass a reference to an array which has 2 elements inside of it. So it's pretty easy. We can just call it, except the shadow which we created might be too short. Might be a silly mistake. We might be experimenting a bit. Either way, the type of x and dftx do not match because here we have an array of float values, of double values with 2 elements, and here we have a single element. That's nice for us because we do create our Rosenbrook definition based on our primary Rosenbrook declaration here. So our shadow is also going to be expected to take a reference to 264 double values. So the compilation process is going to abort here, giving you a type mismatch. Now, we can work around that. If we do not use arrays, like static sized arrays, but instead vectors, which are dynamically sized types, our type system is not able to check this anymore. So we now need to trust the user that if he passes in a second vector as a shadow, that this shadow is going to be large enough because Enzyme is going to update your gradients if you want it or not, right? So if your primary variable has 2 entries and your shadow has 1 entry, the second update is going to be written into, well, some different location. If you have some other variable afterwards, it might get overwritten. If you are lucky, the compilation process is going to not cause any issues, but at runtime you get a seg fault, so at least you're aware of your issues. But in the worst case, we'll just silently corrupt your data. So the official solution for Rust would then be mark all of the functions which we do generate as unsafe, or d_Rosenbrook, at least in the case that we do find dynamically sized types in your function signature. But we obviously don't want to like build a whole Rust scientific computing ecosystem based on unsafe functions, giving up on some of the compiler checks. So we brought this topic up on an earlier conference directly related to Enzyme. And one of the recommendations, which we got by Jed Brown and who's going to talk later, and Valentin Churavi, was a congruency trait. So we could mark types as compatible. We have not implemented that for the Rust side yet. There's a prototype for the Julia front end of Enzyme. And the concept is where your shadow needs to be at least as large as your primal. And in the case that you have some strange input pattern access in your primal function, where you need to make sure that the copy, like the second variable where we will update your gradients, can handle those. We can handle dynamically sized types because we can look up the type of a variable in a compiler, see it's dynamic, and add some runtime checks. For vector, that's pretty easy, but you can obviously not only differentiate with respect to a vector, you can pass in structs, which have pointers, which might point to like different data structures. And following all of those chains is kind of non-trivial. So there's a question like, are we able to automatically always add the correct type of runtime checks? Do we have like a limited set of types, type complexity, which we will handle for you and fall back to unsafe to generate an unsafe function afterwards, if we are not able to prove that we can always catch any user mistakes? So yeah, what is the state of this? That's something I'd also be happy to discuss. And the final solution step obviously would be how to make it available. We want to integrate it into Rust-C. So we want to ship it as a part of the official Rust compiler. We did fill a major change proposal for that, integrate Enzyme into nightly Rust-C, and it actually got accepted. So you can read up details on the link, which I've provided here. We did not merge Enzyme into the nightly Rust-C yet because there are some outstanding issues, but we hope to ship it within, let's say, the next 2 months. So how do we make it available? We currently are blocked on handling Rust enums or union types. The issue being that if you try to differentiate a float variable or an integer variable, those have pretty different gradients. Again, you can't really like see how slight adjustments to an integer would modify an output variable. For the C++ side, we have type-based alias analysis, which can tell us if we have an enum, in which branch do we have like which type of variable. For Rust, the setup is slightly different. The Rust compiler does emit different AVMIR. So in some cases, we are just lost and we can't really understand how enums look like. There are a couple of adjustments, like pretty small ones, even to the compilation process of Rust, which we could do in order to either provide more information or in order to prevent some optimizations which like break the analysis flow for the enums for us. We didn't find the final solution yet. So again, like we are always open to like have new contributors. So if you have some time and would like to work with this project on us, just send me a message afterwards. And well, I think we do have like 2 or 3 more minutes. So if someone has questions, if you have any feedback to our design, I'd be happy to hear them.
Any questions in the chat? Okay.
Thanks, Matthew, for providing the links. So, yeah, I mean, otherwise I'll also be around later in Gathertown if someone is open. Oh wait, I think there was one question, right?
Jonas.
Yes, I've just seen it.
Very interesting stuff. To me, it seemed like the Rust API changed between some of the examples. At the first, you specify the name of the derivative of the function in the derived macro, and then the function to be derived was specified below for the derived macro to be executed on. But later, in the later examples, I believe it was changed around. Did I miss something?
Good catch. So those are indeed 2 different macros. So we do have the option that you either give us a declaration and just put in the name of the primal function, which is going to be somewhere else, like in a different library. Then we can look up that different function and fill your declaration. There's one way. Or you can give us a function implementation and put our macro on top. Then we're going to recognize you already have an implementation, and we're going to generate a second function, which is the differentiating the one which you gave to you. So the macro can handle 2 cases indeed. I think there was a second. As the current design depends on LVM, will it be possible to similar in MIR, though less applicable to other languages? Yes, so we did have some discussion when we ask for integration into the Rust compiler about how we could handle different backends. MIR would be indeed the best solution because it would support crane lift and it would support GCC. But the issue with that is there are some optimizations which are run as part of MIR, but they're comparably small. Usually people default to using LLVM for optimizations. So we would not get a lot of benefits from being at MIR level. At that point, we could probably use Burn or DFDX because they are directly on the user side. So they might even have a nicer user experience than some MIR-based autodiff tooling. We could, however, like the approach with use an enzyme is transferable to a new AD tool, which could be built for GCC or crane lift. So that would probably be the more performance solution.
Any other questions for Manuel? Okay. If you don't have any other questions, oh yeah, so another one.
Oh, yes. So yeah, we've talked about that together already, but maybe it would be interesting for the audience. What about GPUs? So enzyme, I didn't got into details yet because the state of GPU programming in Rust is not as major as in other languages like Julia, but generally enzyme is able to differentiate parallel code. So we can handle OpenMP, MPI, CUDA, and AMD code, so HIP code. We want to extend also for Rayon code, by the way, because AD of parallel code needs some extra optimizations. So once some tooling is able to like compile Rust and CUDA code together, we would be able to differentiate across those like either devices, or we would be able to differentiate across languages. It's just a question of like, which is the best setup to write CUDA code or AMD HIP code in Rust. Once that got sorted out, we can extend enzyme to also differentiate GPU code.